Let's go ahead and start. Let me just say that, I've been extremely happy to have Cameron around for the full 6 months. It's been really, really great having him here. So thank you for coming, Cameron. And so, as you may know, Cameron is our Rothschild professor, or whatever it's called. And, so he'll be talking about left-orderability and 3-manifold groups. So I'm really happy to have him here, not just for the talk, but for the whole thing.
Well, thank you very much, Jake. Yes, and thanks also to your co-organizers, Dorothy and Andrew and Liam, who's not here, but for laying on this wonderful program. It's been just absolutely fantastic. It's been a great opportunity for me to come back to Cambridge, and I've had a wonderful time. And I'm going to have severe withdrawal symptoms I'm going to be here for another couple of weeks, and it's just going to be empty. It's going to be terrible. I'd also like to thank the NM Rothschild and Sons for the support that they've given me during this period. So, yeah, I'm going to talk about 3 manifolds, and again, this is supposed to be a very general talk, so usual apologies to the experts in the audience, many of whom know much more about these things than I do. So bear with me. And I'm going to talk about 3 very different, apparently different aspects of 3-dimensional topology that appear to be related. And so I want to say something about this, but as I say, it's a very general talk and nothing too technical, hopefully. So let's start talking about 3 manifolds. In fact, let's just start talking about manifolds in general. So let's say that all the manifolds I talk about are going to be closed. So let's say a closed N manifold, a compact connected Hausdorff topological space, locally Euclidean. So every point has a neighborhood homomorphic to Rn. So we'll call such a neighborhood a coordinate chart. And I'll remind you that Hausdorff means that every 2 distinct points have disjoint neighborhoods. So having come up with this definition, Poincaré did that, of course. The main example, probably, the canonical sort of N manifold is the unit sphere in Rn plus 1, just the N sphere. So once we have this definition, you'd like to determine all N manifolds up to homeomorphism, up to topological equivalence. So let's start off doing that. So N equals 0. There's only one. There it is. There's only one one-dimensional closed manifold, the circle. So encouraged by this early success, we move on to dimension 2. And here, of course, the well-known sort of paradigm of our classification, there are 2 infinite lists of 2 manifolds, and every 2 manifold is homeomorphic to exactly 1 in this list. There's the 2-sphere, the orientable ones, or the so-called 2-sided ones, the 2-sphere, the torus, the double torus, and so on and so on. The projective plane, which is the quotient of the 2-sphere by the antipodal map that just identifies antipodal points. And then you can take 2 copies of the projective plane and you can remove a disk from each of them and stick them together. You get this and so on. And it's a beautiful theorem, probably finally proved rigorously in the 1920s, although of course it goes back to Riemann and Möbius and so on, that every 2 manifold is homeomorphic to exactly 1 of these. But not only that, I mean, you get a nice algebraic classification as well. Let me remind you that the first homology group of a topological space, it's just going to be some abelian group, and in this case it's going to be some finitely generated abelian group, and you can compute it. If someone gives you a 2 manifold, maybe as a collection of triangles glued together in a certain way, you can compute the first homology, and it follows from the classification that manifolds are homeomorphic if and only if this very simple invariant, this finitely generated abelian group, if they're isomorphic. So not only is there a complete list, but there's an algorithm for telling you where a given manifold lies on that list. And in particular, the 2-sphere is characterized by the fact that it's the only 2 manifold whose first homology is 0. Okay, so that's very nice in dimension 2. Now in dimension 4, it's an old theorem of Markov that you just can't hope for a classification. The homeomorphism problem for n manifolds is algorithmically unsolvable. There's no algorithm that will take as its input two even piecewise linear n manifolds and tell you whether they're homeomorphic or not. So people don't study higher dimensional manifolds. Well, they do? Oh. Yeah, so, of course, you just ask different questions. But anyway, but a naive classification, as in dimension 2, is simply logically impossible. That leaves dimension 3, which is interesting kind of, it occupies this interesting sort of space between the dimension 2, where there's this very nice, very sort of nice countable list, and the sort of logically impossible world of dimensions 4 and higher. So again, here, Poincaré realized, well, he had already introduced the fundamental group of a space. So this is a group whose abelianization is the first homology group, but it's typically a non-abelian group. And he realized early on that there were many 3 manifolds that had the same first homology, but different fundamental groups. And in fact, eventually he showed that there's actually a 3 manifold whose first homology is 0. But it's not the 3-sphere because its fundamental group is non-trivial. So this is the famous Poincaré homology sphere. And again, interestingly, he originally conjectured that any 3 manifold with first homology 0 should be the 3-sphere, but he quickly realized that wasn't true. So, there's Poincaré. So homology isn't good enough to classify 3 manifolds. Let me say something about knots, which are sort of really part of 3-dimensional topology. And I want to emphasize that there are an awful lot of 3 manifolds. You're not going to get a simple list like you do in dimension 2. So the theory of knots started in the really started in the second half of the 19th century, inspired, as many things in topology are, by physics. So this was the theory of vortex atoms, sort of popularized by Lord Kelvin. The idea was that an atom was a knotted vortex in the ether, which was this fluid that permeated the whole universe, and different elements corresponded to different knotted vortices. See, Helmholtz had proved that a sort of vortex in a fluid had a certain stability, and so this was an appealing sort of property of atoms, which you didn't have to assume, you could actually prove it. And so Lord Kelvin asked his friend Peter Guthrie Tait, does anybody know anything about knots, And Tait said, well, I'm not sure, but maybe I could look into it. So he spent the next 20 years of his life sort of studying knots and tabulating them in particular, trying to see, are there enough knots with small crossing number to account for the elements. By the way, Tait, he went to Peterhouse, Cambridge man. He was senior wrangler in 1852. And Erica told me that the other day she was at Peterhouse. There's a desk there in which P.G. Tait has carved his name. So, so he tabulated. So here's one of his tables. The first 7 orders of knottiness. So the order of knottiness is what we would call the crossing number these days. And you see, this first 7 orders, it starts at 3 because there aren't any non-trivial knots with order of knottiness less than 3. So there's 1 of order 3, 1 of order 4, 2 of order 5, and so on. This is up to 9. So basically, he's classifying knots up to 9 crossings. And here's some 10-fold knottiness. There's an awful lot of knots. So why am I talking about knots? Well, apart from the fact I love knots, but you can associate with a knot many different 3 manifolds. So this just gives you an idea of how complicated the world of 3 manifolds is. So let me just mention one way of associating 3 manifolds to knots. It's with perhaps many people are familiar with Dane surgery. That's perhaps the most common way of doing that. But earlier than that, this construction of just taking a double branch cover was popular. So if you take a knot And so, you know, you think of a knot, by the way, is, yeah, we just have this circle somehow embedded in R3. It's convenient to compactify R3 to S3. Okay, so we've got this circle sitting in S3. If you remove it, you get the complement X. And the first homology of this is just Z. It doesn't matter what the knot is. It's just Z, and it's generated by a meridian, which is a little curve that just links the knot simply like this. Well, what this implies is that the fundamental group, remember, maps onto the first homology, which then maps to Z. So there's a canonical map to Z2, and you get an induced twofold cover of X. And because the first homology is generated by the meridian doesn't lift, but it square lifts. And so up in this cover, the projection map wraps this circle upstairs twice around this circle. The upshot is that you can sort of glue in a circle upstairs and glue in the circle, the knot K downstairs, to extend this covering projection to a branch covering from a closed manifold, the kind of manifold we like, to the 3-sphere. So this manifold sigma K, this is the double branch cover of the knot. And as I say, I mean, I'll come back to this a little bit later, but the main point I want to make now is that you see that for every knot you can associate this manifold. And typically different knots give rise to different manifolds. And so the moral is that 3 manifolds are at least as complicated as knots. So there's an awful lot of 3 manifolds, because there's an awful lot of knots. Okay, so you're not going to get a really simple classification like you do in dimension 2. Okay, let's get back to the fundamental group. So let's just again just focus on the case of an n-dimensional manifold. Look at the universal covering space. That will be some manifold with, well, it won't be closed necessarily, but it'll have trivial fundamental group. And the fundamental group acts freely on this space, and the quotient is the manifold. This is really the way Poincaré first thought about the fundamental group. I mean, nowadays we define it in terms of homotopy classes of loops, but really you should think of it as it's this group that acts on this universal covering, and this quotient is the manifold. So if we go back to 2 manifolds, there are there's a basic dichotomy. Either the fundamental group is finite or it's infinite. Well, of course, there aren't too many 2 manifolds with finite fundamental group. There's just the 2-sphere and the projective plane. And there, the universal covering is the 2-sphere, and this group acts on it. You see the projective plane acts by the antipodal map with quotient. And all the others have the universal covering is the plane. And a similar picture actually holds in dimension 3, very similar. Under the assumption, so let's always assume, I'm going to always assume that our 3 manifolds are orientable. That's not a big assumption. And irreducible. So irreducible, see, every 3 manifold contains lots of 2 spheres. I mean, just take some coordinate chart. That's R3, so there's going to be a 2-sphere in there. But you say a manifold is irreducible if those are the only 2 spheres in the manifold. And there's a very nice theory due to Knaser and Milner about decomposing 3 manifolds into unique sort of irreducible pieces. And so it's really no big loss of generality to assume our manifolds are irreducible. So I'll do that for the rest of the talk. If I talk about a 3 manifold, it'll always be orientable, irreducible, and closed. And now, as a consequence of the geometrization conjecture, just one very basic, not very detailed consequence, proved by Perlman, of course, that again you get a similar dichotomy for 3 manifolds, irreducible 3 manifolds. Either the fundamental group is finite, in which case the universal covering is a 3-sphere, and the fundamental group is acting, and in fact it's acting linearly. It's acting just, as a subgroup SO4, and the quotient is R3 manifold, or the universal covering is R3. Of course, the geometrization conjecture says much more than that, but this is just a very broad brush conclusion. For future reference, it's not hard to prove that if the universal covering is R3, then in fact the fundamental group, as well as being infinite, it's actually torsion-free. Let me give an example of this first case, because these are very some of the first 3 manifolds that were looked at historically, the lens spaces. So if we take 2 relatively prime integers with p at least 2, p and q, then the cyclic group ZP acts on a 2-dimensional complex vector space by just rotating one copy of C through 2 pi over P, and then the transverse copy through 2 pi Q over P. And of course the origin is fixed, but this will be a free action on the unit sphere, and so the quotient will be a 3-manifold, closed 3-manifold. So this is the length space LPQ, and the fundamental group is, of course, this group that's acting on the 3 sphere, ZP. So these were some 3-manifolds that were looked at a long, long time ago, some of the first examples of 3-manifolds. And again, after Poincaré had proved that there were many 3-manifolds with the same homology but different fundamental group, a very natural question was, well, maybe the fundamental group determines the 3-manifold. The homology isn't enough. And so that's an obvious question. And of course, well, the answer is no. You see, these length spaces are very simple counterexamples, because the fundamental group depends only on P, but it turns out that the homeomorphism type also depends on Q. In fact, it was first proved by Alexander back in 1919 that L5.1 and L5.2 were not homeomorphic, although of course their groups are isomorphic. So, but again, this is an example of an assertion, that's false, but it's only just false. I mean, the counterexamples are these very, very simple manifolds. And in fact, again, the geometrization conjecture implies we now know that under our assumptions on 3-manifolds, in fact, as long as you stay away from length spaces, the fundamental group does determine the homeomorphism type. So the fundamental group is essentially a complete invariant of a 3-manifold. So any property of the fundamental group is going to be crucial. Any property of the 3-manifold is going to be reflected in the fundamental group. I always think I've said this before, but I always think there's a useful lesson to be derived from this, that, if you make a conjecture and you find out it's false, don't worry. Just keep going, Maybe the counterexample was really simple, maybe that's it, I always give the example that, 2 is the only odd prime, even prime. So 2 is the only prime that's not odd, right? So, yeah. Of course, a famous special case of this is the Poincaré conjecture, that the only 3-manifold with trivial fundamental group is the 3 sphere. So here's Perlman. This was the Clay Millennium Prize problem that he declined the prize for, the Poincaré conjecture. So the fundamental group is the key thing. So having established that, then let me talk a little bit about a property of groups, left-orderability. So a non-trivial group is said to be left-orderable, and I'll abbreviate that to LO, if there's a total order on the group. And let me remind you that's just a transitive relation that has the property that for any 2 distinct elements, A and B, either A is less than B or B is less than A, and exactly one of those holds. So that's just a set theoretic notion, but the group theory, the group structure comes in by insisting that this be left-invariant. So it's invariant on the left multiplication. If G is less than H, and FG is less than FH. So let me just make a few elementary remarks about that. Obviously, the additive group of reals with the usual order is that's left-orderable. Of course, that's bi-orderable because it's an abelian group. Left-orderability is inherited by subgroups. By the way, it's just a convenience to not regard the trivial group as being left-orderable. That's just a useful convention. Certainly not all groups are left-orderable. In fact, being left-orderable implies that you're torsion-free, and that's very easy to see. If you've got an element of a group, if it's not the identity, let's assume it's greater than the identity, without loss of generality. Multiply this on the left by G, and you get G squared is greater than G, but G is greater than 1. And so G squared is greater than 1. And so all the positive powers of G are greater than the identity. So, and similarly, if it's less than 1. So certainly, but of course, there are also torsion-free groups that are not left-orderable. There's a very nice dynamical characterization of left-orderable groups, at least for countable groups. A countable group is left-orderable if and only if it's isomorphic to a subgroup of this group, the group of orientation preserving homeomorphisms of the real line to itself. So that's very nice. Let me at least prove one direction. Let me prove that this group is left-orderable. And the other direction is not much harder, but so why is this group left-orderable? Well, here's one proof not the best maybe, but just choose any countable dense subset of the real line. Suppose you've got two orientation-preserving homomorphisms of the real line that are not equal. Well, they must differ on one of these elements in this dense subset. So just choose the least index in this numbering such that they differ. Okay, well, these are two distinct real numbers, so one is less than the other. And so let's declare that G is less than H if and only if Gxn is less than Hxn. And it's an elementary exercise to prove that this is a left order. So this shows many things. It shows that there are uncountably many left orders on this group, and so on. Anyway, this group is left orderable. This will come up in some of the later things I'm going to say. So one might ask, I mean, having decided that the fundamental group for 3-manifold essentially tells you everything about the 3-manifold, we might now ask which 3-manifold groups are left orderable. And there's a very nice theorem of Boyer, Rolfson, and Wiest that says that for a 3-manifold, under my assumptions, the group is left orderable if and only it has a left orderable quotient. So that's very useful. And so, for example, just a very basic corollary of that is that if the first homology is infinite, you see the fundamental group maps onto H1. If this is infinite, H1 will map onto Z, but Z is left orderable. And so manifolds with infinite first homology, the fundamental group is left orderable. So the only interesting case is when H1 is finite, in which case one says that, well, in which case the manifold has the rational homology of the 3 sphere. So that's called the rational homology sphere. So one might ask this question: for which rational homology spheres is the fundamental group left orderable? Well, again, if the fundamental group is finite, for example, the lens spaces, obviously it's not left orderable because it has torsion. Okay. When pi1 of m is infinite, well, it's kind of interesting. Sometimes it is, sometimes it isn't. And we'll see that it's actually related to some other considerations. So first, then, we'll see, let's talk a little bit about foliation. So I'm just going to always talk about codimension 1 foliation. So let's say, again, this is a very rough sort of definition. So if you've got an n-dimensional manifold M, so a codimension 1 foliation, it's a decomposition of M into n-1 dimensional leaves. So the point is that there are coordinate charts which have this kind of product structure, just Rn-1 across a point, and these are compatible. The product structures agree as we go from one to the other, and so these horizontal slices sort of join up to form these n-1 dimensional leaves in the manifold. And I'm going to assume that everything's oriented, and there's a coherent normal orientation here, and so the leaves are orientable, and so on and so on. A very simple but uninteresting example would just be an n-1 dimensional manifold across the circle. So if I can just take a surface across S1, and that's a nice 3-manifold that has a foliation, but that's not really that interesting. Well, it turns out that every 3-manifold has a foliation. This was proved in 1965 by Licorice and independently Novikov and Zishang. Ray may still remember. Yes. So a good example here is to wonder, well, S3, does S3 have a foliation? And the story is that Ehresmann gave, as a problem to one of his graduate students, George Rabe, prove that S3 doesn't have a foliation. So Rabe proved that it did have a foliation. And he introduced a thing called the Rabe foliation of a solid torus to do that. By the way, Ehresmann had 76 PhD students, so he couldn't give them all problems that were correct. So that was the famous Rabe foliation of a solid, and using that you can then foliate every 3-manifold. So to get some mileage out of this, then you need to impose some additional condition, and there's this notion of tautness, which I believe was introduced by Dennis Sullivan. So you say that, again, I'm only talking about 3-manifolds now. You say that this foliation is taut if there's a loop in the 3-manifold that meets every leaf, and it meets every leaf transversely. Well, so now it's not true that every 3-manifold has a taut foliation. I'll abbreviate that to TF. For example, if it's a theorem of Novikov that if you have a taut foliation, then at least pi1 is infinite. And just as a first little bit of a suggestion of maybe a connection of this with left-orderability, There's a theorem of Gabay that says that if the first homology is infinite, stronger condition, then in fact M does have a tort foliation. So remember, if H1 of M is infinite, then pi 1 of M is left-orderable by the Boyer-Rolson-Weiss theorem. Let me point to a slightly more refined connection between left-orderability and foliation. So if you have a tort foliation on the manifold, you can go up to the universal covering and lift the foliation. Now, the universal covering is going to be R3 because pi 1 of M is going to be infinite. This was known before the geometrization, but anyway, whatever. Now, up there, you could identify each leaf to a point, and you get this, you get this leaf space. Now, you see, you could have done this down here, but chances are you're going to get some real mess. You get some horrible topological space that's not even T1. It's totally uninteresting. But it turns out that in dimension 3, if you go to the universal covering, because of results of, I guess, Novikov and Palmera, that up in the universal covering, this leaf space, it is going to be a one-dimensional manifold. It's going to be a simply connected, in other words, a connected one manifold with pi 1, with trivial pi 1. So the obvious picture is that up in R3, you just get a foliation by horizontal planes. You do, in fact, get a foliation by planes. The nice picture would be they're just all horizontal, just homeomorphic to the horizontal foliation, in which case the leaf space would be the real line. But the catch is that although it's a one manifold, it's not necessarily Hausdorff. Because remember, right in the beginning, we actually threw this condition in the definition of a manifold. You'd better do that. By the way, there's a textbook, which I won't name, which proves Poincare duality for manifolds and doesn't assume Hausdorff. And so the exercise is to go through the proof and find out where they're secretly using Hausdorff, because it's not true for non-Hausdorff manifolds. Anyway, so it's easy to forget. But anyway, these are examples of non-Hausdorff manifolds, sort of one-dimensional manifolds even that naturally arise. So let me explain this a little bit. So here's a picture one dimension lower. This is a foliation of the plane by lines. And you see, you could have something like this. Many people recognize this is very closely related to the Rabe foliation. You see that in the leaf space, if you identify each leaf to a point, these two leaves, lambda and lambda prime, they don't have disjoint neighborhoods. Every neighborhood of this guy, you see, is going to contain one of these leaves sufficiently far down here, and same with this guy. So this is a natural sort of situation where you get non-Hausdorff manifolds. Anyway, in nice situations, the leaf space up here is Hausdorff, and so then it will be the real line, and one says that in that case the foliation is R-covered. So foliations of three manifolds certainly won't always be R-covered, but if they are, it's nice because one then has this theorem. Let me just write the whole thing. That if you have a tort foliation on a three manifold, so here's a couple of conditions under which it implies that the fundamental group is left-orderable. Either the foliation is R-covered, or the first homology is zero. M is an integral homology sphere. So let me prove the first part. So you see the fundamental group acts on, we've got this foliation F on M. We lift it up to the universal cover. Pi 1 of M acts on everything. So in particular, it's going to act on the leaf space up here when you identify each leaf to a point. So, but by hypothesis, the leaf space is the real line. So, and because of my orientability assumptions and so on, this is an orientation preserving action, and it's also non-trivial because the quotient is compact, And so you get a non-trivial homomorphism from the fundamental group to the orientation preserving homeomorphism of R. Well, we've seen that this group is left-orderable, and so the image of this homomorphism is a subgroup. That'll be left-orderable. Well, therefore, this means that pi 1 of M has a left-orderable quotient, and so it'll be left-orderable. So, really nice foliations imply a left-orderable. Let me not say much about this, but there's a similar, well, no, actually rather different, actually, but ultimately similar argument in the case when the first homology is zero. It turns out that there, you get an action of the fundamental group on the circle, this Third universal circle. The details of all this were done by Caligari and Dunfield. So the fundamental group now has a non-trivial representation into the orientation-preserving homomorphism of the circle. But that's not good enough. You want to lift that up to homeomorphisms of the real line, and it turns out that if the first homology is 0, you can do that. So anyway, that's a very brief, some remarks about this. And again, so there you are. If you have a foliation, then under nice conditions at least, the fundamental group is left-orderable. So that's two of the ingredients, left-orderability, foliation. The third ingredient starts with the idea of a Hegardt splitting of a 3-manifold. So 3-manifolds were proved to be triangulable back in the 1950s. And as an easy consequence of that, every 3-manifold has what's called a Hegardt splitting. So that is a decomposition of the manifold into two pieces, H and H prime, and they're homeomorphic. Each of them is homeomorphic to this so-called genus G handlebody for some G. So a genus G handlebody, it's just this picture here. So you take a orientable surface of genus G, here G is 3, you sit it in S, or sit it in R3 in the usual way, and it bounds this 3-manifold with boundary. So that's a genus G handlebody. And so you can always take two copies of this and glue them together along their boundary. So H and H prime intersect just in their boundary, and you get a 3-manifold. And every 3-manifold can be obtained in that way for some G. For example, the lens spaces that we've talked about, they are precisely the ones you get by where the genus is just 1. Well, you also get S3 and S1 cross S2, but generic, you'll get a lens space. So such a Hegardt splitting, the pair, the 3-manifold and the surface, is actually determined by what's called a Hegardt diagram, which consists of the surface F, this genus G surface, and two collections of disjoint simple closed curves. Alphas, so there's G disjoint simple closed curves, alpha 1 through alpha G, and there's another G disjoint simple closed curves, alpha 1 prime, and so on. So here they are. This is the kind of picture. They are homologically independent disjoint simple loops in the boundary, and they sort of define the handle bodies H and H prime in the sense that every alpha I bounds a disk in the handle body H, and every alpha I prime bounds a disk in the handle body H prime. So you've got red circles and green circles, and there we are. We've got this surface F, and we've got the G red circles, G green circles, and that determines the 3-manifold. Well, of course, the catch is that these two boundaries are identified by some homeomorphism. So although we can draw each of these systems as looking up to homeomorphism standard, if we try to draw them on the same surface, at least one of them is going to be probably rather complicated. So we can always draw this diagram so that the green curves look standard. So here's an example. See, genus 2, there are two green curves. And then, well, okay, there are two red curves. Actually, there's a red and a blue curve, right? Two red curves would be too confusing. So there's a red and a blue. So those are the alphas, alpha 1 and alpha 2, and these are the alpha 1 and alpha prime. So this determines some 3-manifold. In fact, many of you will recognize that this is the Poincare homology sphere. I mean, this is essentially the way Poincare described his famous manifold that had trivial first homology, but non-trivial fundamental group. So that's a Hegardt diagram. And there's the end of Poincare's famous paper on this. He describes this example, and he says there's one question left. Can you make the fundamental group trivial and still the manifold is not simply connected, meaning homeomorphic to the 3-sphere? And then he explains that what he means by that is, can we choose these two curves, alpha 1 and alpha 2, such that blah, 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 okay. And then he says, but this question would lead us too far afield. So he had the good sense to stop. And, right. So these Hegardt diagrams were used by Oswald and Szabo in 2003 to define this Hegardt floor homology theory, which, I mean, this is the sort of end of a long development, really starting with Donaldson's work back in 1982, Donaldson's gauge theory on 4 manifolds, and then also Fleur's Lagrangian Fleur homology that he used to attack the Arnold conjecture. And anyway, there's a long history. So what Ozat and Szabo did, they said, well, suppose you have a Hagar diagram of a, let's say it's a rational homology sphere. So we've got this surface of some genus, and we've got these two collections of curves, the red curves and the green curves. Well, you can take the G-fold product of the surface with itself, and actually you take the symmetric product. Let's factor out by the symmetric group. So this is some real 2G dimensional manifold. And then the product of these curves, there are G of them. So this is just a G-dimensional torus. This is another G-dimensional torus. And they're sitting in this 2D G-dimensional manifold. And so this is reminiscent of Fleur's Lagrangian Fleur homology. They said, well, let's take a vector space. Let's just say a vector space over with two elements. So we're going to define a chain complex. So the change is just this vector space, and the basis is just the intersections of these two tori. And of course, you can describe that just in terms of the intersections of the curves on the surface. The differential is, of course, much harder. There, you want to use Whitney disks. So you want to look at disks. You want to look at a pair of points in this intersection. You want to look at disks such that the boundary of the disk contains an arc joining the 2 points in T and another arc joining the 2 points in T prime. I've run out of batteries.
It's the end of the program.
Right. Okay. All right, I'm recharged. All right. Yeah, anyway, and so of course, as many of you know, you have to, I mean, your analysis has to come in here. You first put a complex structure on this, and then these guys will be totally real submanifolds, but that's not good enough. You have to put an almost complex structure and use pseudo-holomorphic disks rather than holomorphic Whitney disks. Of course, it turns out by Sarkar and Wang showed that you could describe this purely combinatorially just from the Hagar diagram. But basically, it's an analytic invariant. So anyway, you get a chain complex, and as Ozat showed, the homology of this chain complex, let's call it HF hat, there are various variants. That depends only on the manifold. It's independent of the Hagar spring. It's independent of the alphas, and so on and so on. And it's also quite easy to see that the dimension of this, once you have the definition, is at least the order of the first homology. Remember, I'm assuming this is a rational homology sphere, so this is just some finite abelian group. Ozat and Szabo defined a manifold to be an L space if you have equality here. And this was motivated by the fact that lens spaces are L spaces. So one of the first applications of this Hagar-Floer homology was to, like the Berge conjecture about which Dane surgeries on knots give rise to lens spaces. And I guess Ozat and Szabo noticed that they really only used the fact that this was an equality for lens spaces. And so all the proofs automatically work for L spaces as well. So lens, and more generally, anything with finite fundamental group is an L space. So here we have this other notion in three-dimensional topology coming from this Hagar-Floer homology, the notion of an L space. And as a fundamental theorem by Ozat and Szabo relating this to taut foliations, that if a manifold has a taut foliation, then it's definitely not an L space. So this uses, contact structures and symplectic four-dimensional topology and so on and so on. It turned out that there were some technical smoothness assumptions needed for the original proof, but these were removed quite recently by Bowden and Kazez and Roberts. So we can now state this without any sort of conditions. So with all these ideas lurking around, it's natural, perhaps, to conjecture that they're all equivalent. So one conjectures that for a three-manifold, an orientable irreducible three-manifold, rational homology sphere, let's say, or I mean, you don't have to say that. The fundamental group is left-orderable if and only if the manifold has a taut foliation, if and only if it's not an L space. So I guess this equivalence was explicitly conjectured by Boyer and Watson and myself, and this was explicitly conjectured by Uhash, I think. But I mean, the ideas were all floating around, obviously. It's a natural statement to think about. And it's known to be true for many classes of 3 manifolds. Well, several, maybe not many. It's known for Seifert-Fibert spaces, graph manifolds, but in general it's wide open. And many people here have been involved in the proofs for those classes of manifolds. Let me just go back to double branch covers and knots. In fact, let me go to a very simple class of knots, the rational knots, that are parameterized by a rational fraction p over q. So if I take some rational number p over q, actually I should take p to be odd if I want to get a knot. I can take the continued fraction expansion, a1 plus 1 over a2, and then using these terms in the expansion, I can then draw a picture. So perhaps an example is the best way to explain this. So 3 over 1, well, that's just 3, right? And so I draw 3, 1, 2, 3. Then I close it up. So this is the rational knot corresponding to the rational fraction 3. 5 over 2 is 2 plus 1 over 2. So here I have 2, and now I have another 2. And notice I make it sort of alternate there. So that's the knot corresponding to 5 over 2. Here's another one, 13 over 5. I can write it as 2 plus 1 over 2 minus 1 over 3. 2, 2. But now this is minus, so I don't make it alternate there. So this is a very nice class of knots. It was studied a long time ago. And remember we talked about the double branch cover of a knot. Well, the double branch cover of the PQ rational knot is just a length space LPQ, it turns out. So I alluded to this definition. Of course, many of you know it anyway, but you say that a knot is alternating if it has a diagram where the crossings alternate over, under, over, under. And these rational knots are alternating. You just take a continued fraction expansion where all the terms are positive. So for example, 13 over 5, see I previously did it with this, and I didn't get an alternating diagram. But actually, there's a different continued fraction expansion. Now I get an alternating diagram. And it's the same knot, you see. So these are alternating. So these guys are alternating knots, and their double branch covers are length spaces. And length spaces, of course, are the sort of paradigm L spaces. By the way, here are some nice alternating knots. Maybe they're not knots. I mean, it was long observed that if you just have an immersed circle or a bunch of immersed circles, just like a 4-valent graph, you can always make the crossings alternate over, under, over, under. That's a nice elementary exercise if you're not quite sure why that's true. And so, of course, artists have done this for a long time. This is a Pictish example. This is a Celtic example, around about 900, I think. So you can always make these alternating. There do exist non-alternating knots. In fact, most knots are non-alternating, although most of the small ones are alternating. This is the first one that appears in the knot tables that I was alluding to when I talked about Tate. So again, you know, if you haven't thought about this, obviously this is a non-alternating diagram, but why is it non-alternating? I mean, why is it not non-alternating? Maybe it has an alternating diagram with 100 crossings, you know. Well, it doesn't, but you have to prove that. This, by the way, brings us to the Reverend Thomas Kirkman. So when Tate was doing his tabulation of knots back in the second half of the 19th century, he was helped by this, the Reverend Kirkman, who was a combinatorist, and he provided Tate with just with the 4-valent graphs without the crossings sort of introduced. And Tate then sort of made them into knots and tried to figure out which were different. So Kirkman was definitely a character. He had very strong opinions on many things. I was like, the very first sentence of his very first paper on knots is his definition of a knot. And we know how important it is. If we want to study things, we've got to get the definition right. So, by a knot of edge crossings, I understand a reticulation of any number of meshes of 2 or more edges, whose summits, all tesseraces, are each a single crossing, as when you cross your forefingers straight or slightly curved, so as not to link them, and such meshes that every thread is either seen when the projection of the knot with its end crossings and no more is drawn in double lines, or conceived by the reader of its course when drawn in a single line, to pass alternately over and under the threads to which it comes at successive crossings. So that was Kirkman's definition of a knot. So basically, he thought of a knot as an alternating diagram. In fact, he says, he says, I can't understand. Professor Tate, he claims that, you know, that that a knot is this sort of topological thing and you can deform it, and that Kirkman didn't understand that. To him, a knot was just a diagram. And by the way, I think he's telling us that these are not tesseraces, they're tesserakes. From the Greek, you see. He says, in the same paper, he says he can't stand people saying polyhedral. Why is the H there? It should be polyhedral. He says you might as well say periodic. Put an H in that, you know. So he had very strong opinions on many things. And by the way, actually, this is a good time to remember that you may have noticed, I'm sure the experts would almost certainly have noticed that, and this takes a while, that when I went back to Tate's, oh, there we are, sorry, okay, wait. There must be a quicker way to do this. Okay, yeah, actually, you'll see that there aren't any crossings here. These are just immersed circles. Because Tate was only interested in alternating knots at this point. And so you don't have to label the crossings. These are all alternating. So it wasn't until a bit later, somebody called Little, who actually started looking at non-alternating knots. Anyway, so the first tables were really just tables of alternating knots. And that was Kirkman. So where are we? Okay. Right. Now we know what a knot is. Okay. So, so as I said, remember the So a rational knot, the double branch cover is a length space. So more generally, Ossoff and Schaber showed that if you have an alternating knot, then the double branch cover is an L space. And well, okay, it's an L space, and so therefore, by the theorem I mentioned earlier, this manifold does not have a taut foliation, right? But if the conjecture that I mentioned is true, then the fundamental group should be not left-orderable. Well, so indeed, this turns out to be true, that if you have an alternating knot, then the fundamental group is in fact not left-orderable. So we proved this, and yes, Boyer and Watson and I proved this in 2011. Also proved by Josh Green and Levine and Llewellyn. Okay, so again, this is some very, very mild evidence, extremely mild, because these are rather special manifolds, mild evidence for this conjecture. But having started talking about double branch covers, and we see that, you know, they do sort of come up reasonably naturally, we might as well look at n-fold cyclic branch covers. I mean, for every n at greater than or equal to 2, you can do the same construction I mentioned. Take the n-fold cyclic cover of the knot complement and then sort of complete the covering projection to a branch covering. So we have these segments. And so you could ask, you know, how do these manifolds, for a given knot, you know, how do these behave with respect to these properties? Fundamental group being left-orderable, existence of taut foliations, or not being an L space for arbitrary NK. And so let me just mention some relatively recent results in conclusion that say something about this. So again, I would remind you, if you haven't heard of this before, that the signature of associated with a knot, you can look at an orientable surface spanning the knot, and you can use that surface to associate a symmetric bilinear form, which is sort of non-singular. It's determined, it is actually the order of the first homology of the double branch cover. Anyway, this form has a signature. You know, over the reals, you can just diagonalize it, some pluses and some minuses. The difference is the signature. And it turns out that if for any rational law, the double branch cover, you see, in fact, the double branch cover is a length space, you see, obviously, and it's not left-orderable. But there are many rational knots that, in fact, this holds for all the n-fold cyclic branch covers. For example, the figure 8 knot, which was the knot 5/2 that I drew a while ago. Not only is the two-fold branch cover an L space, but all the branch covers are L spaces. And in fact, the groups are all not left-orderable. But they all have signature 0. All these examples have signature 0. And there's a reason for that. It's because it's not true. if the signature isn't 0. So the theorem I proved recently is that if you have a rational knot, and if the signature is not 0, then in contrast to this, in fact, if n is sufficiently large, the fundamental group of the n-fold cyclic branch cover is left-orderable. Well, this raises many questions. An obvious question, is this true for all knots? Does the non-vanity of the signature imply that eventually this branch cover becomes left-orderable? And also, what about the other two properties that are supposed to be equivalent to this? Existence of a taut foliation and not being a null space. And again, let me just mention one theorem here. Again, I'll remind you that the genus of a knot is the minimum genus of any oriental spanning surface, and the absolute value of the signature is at most twice the genus. That's easy, that's obvious. And something that Michel Boileau and Steve Boyer and I proved just quite recently. If you strengthen the assumption that the signature is non-zero to the assumption that it's maximal, in other words, its absolute value is equal to twice the genus, then we get this not an L space property for insufficiently large as well. So remember, if the signature is non-zero, you get that this is left-orderable, but here you get this an LS property as well, but it's a stronger assumption. But again, so I think there are lots of questions here. What about taut foliations on these things? What about other knots? I mean, I think there are a lot of good questions. In the absence of a general proof of the conjecture, you could look at special classes of manifolds and wonder what's going on and try to see some structure in the behavior of these properties. Let me just finish by saying that Nathan Dunfield, a couple of years ago, examined over 250,000 rational homology spheres with respect to these properties I'm talking about, and he found no counterexample to the conjecture. So, I mean, maybe that's some evidence. Now, some of the properties he wasn't able to establish one way or the other, but for all the ones where he could establish, is it an L space or not, and is it left-orderable or not, does it have a taut foliation or not? The conjecture seemed to hold up. So I just think this is an interesting set of ideas, because you see, I mean, any general proof of the conjecture is going to have to reveal some interesting deep connections between these things, I think. Up to now, many of the proofs of the truth of the conjecture for several classes of manifolds consist of sort of verifying one property and then verifying the other property. But obviously there should be some really, obviously the Oz-Vasabo theorem that if you have a taut foliation, then you're not an L space. That is a deep structural connection. But what's lacking are such connections with left-orderability and with L space and taut foliations in the other direction. So I think there's lots of scope for problems here, and so I encourage people to think about this conjecture. Thank you.
Questions?
How does one disprove that a group is left-orderable?
Well, actually, yeah, that is something that can be done. I mean, if a group is not left-orderable, then you will eventually discover that if you work hard enough. No, I mean, no. In fact, Nathan Dunfield has a program that will take as its input a finite presentation, and it keeps turning around. And if the group is not left-orderable, it will eventually stop and say it's not left-orderable. But of course, it may go on for a long time, and you don't know. So it is. You just look at longer and longer words, words of longer and longer length, in the generating set, and you want to. I mean, you look at the semi-group generated by those, and anyway, it's a finite process. So, on the other hand, or you could just be really clever and look at the relations and say, oh, look, if this is greater than this, then I get a contradiction. So this must be, but then I get another contradiction. So there are arguments like that, but. And it's what some people have done, actually. They've used a computer to prove that certain groups are not left orderable, and then examine what the computer did and get a proof that's comprehensible to a human being, you know. But I think there's no sort of simple answer. I mean, you can sometimes do it, but sometimes it's very hard. Yeah. Yeah.
Was that
Oh.
stated for 3-manifold groups, checking if they're left orderable, or is that just arbitrary finitely presented groups to check?
Arbitrary finitely presented group. Yeah. Yeah.
How was
It's-
the relevance?
Sorry.
I wanted to ask how the relevance of left orderability was discovered.
Yeah, that's. I'll tell you how it was discovered. I mean, it was. I think it goes back to the work of Rachel Roberts and John Sharesian. That's right. They were proving that there were certain 3-manifolds that didn't have taught foliation. I mean, manifold infinite fundamental group and so on. And so they, yeah, I mean, it was. I mean, so in doing that, they proved that the group wasn't left orderable. I mean, it was much harder than that because they had to prove that the group in question didn't have a non-trivial action on one of these non-Hausdorff 1 manifolds. You see, but in particular, they showed that. So in particular, they showed that it couldn't act on R, and therefore it wasn't left orderable. So I think that was the first time that left orderability. The relation between left orderability and foliations came up, yeah.
The- Being left orderable has something to do with acting on R.
Yeah.
That is, acting by diffeomorphisms on S1 have any role in this story?
Yeah, well, there you get what's called a circular order. You know, you can. So I mean, there's an
You
obvious.
get a torsion, for instance.
Yeah, exactly. I mean, Zn is circularly ordered. But yeah, so there's the notion of a circular order where, you know, it's the obvious definition. I mean, you can just make it up. You know, the triples rather than pairs. You know, and it should be left invariant. There are some manifolds, 3-manifolds that don't even have an action on Homology plus S1 though, like the Weeks manifold. That was something that Caligari and Dunfield showed. So it doesn't even have a circular order.
Do you have any sort of effective control on this last theorem about when the genus is equal to the signature? I mean, is there any effective control on when you get a non-L space in terms of, you know, how far up and in do you have to go?
Yeah, you can. I mean, you get estimates based on the roots of the Alexander polynomial. I mean, so yeah. In fact, you can compare the estimates that you get with what you get for left orderability. Yeah, you were asking about not L space. Yeah.
Well, no, I was asking about left order.
Oh, you're asking about left orderability. If the signature is non-zero, yeah. Yeah, you can get estimates, you know, based on the, well, for rational nodes, just based on the roots of the Riley polynomial. I mean, based on the Riley polynomial, so you can get estimates of when, at what point it kicks in. But they're not best possible. I mean, so that's another question. I mean, okay, so look, I mean, even for the simplest 5-crossing knot, I've talked about the. I mean, the trefoil is a torus knot. We know all about that. The figure 8 knot, we know all the branch covers are L spaces and not left order. The next knot is the 5-crossing knot 5-2, and even there we don't know exactly when you know the left orderability kicks in. It kicks in certainly no more than 9, but it looks like it should kick in at 6. So for 6, 7, and 8, this gets back to the question that Matt asked. We suspect the group, you know, is left orderable, but we don't know. I mean, I asked Mark Culler to run this on Nathan Dunfield's program, and it's still running as far as I know. I mean, you know, so probably left orderable, but that's not a proof, you know. So.
Let's thank Cameron again.